Hi, everyone. I'm sure we're all still getting settled, but thank you for being here today. Welcome to the Data Validation for Hosting Capacity Analyses webinar, hosted by the National Renewable Energy Lab and the Interstate Renewable Energy Council. I'm Jess Townsend with the NREL Communications Department. I'm just going to get us started with a couple of housekeeping items before turning the event over to our panelists today. As you settle in, please drop your name, the organization you represent, and how you interact with hosting capacity analysis in the chat so we can all get to know each other. I'm going to go ahead and drop this prompt in the chat as well for you because I'm going to keep us moving since we only have an hour together today. As we get started with those introductions, I'm going to jump right into a few housekeeping items. If you experience any technical issues, feel free to message me as the host using the chat panel. We also encourage you to interact with our panelists today and with each other through that chat box, and you can submit questions via the Q&A panel as well. We will be answering as many of those questions as possible in the last 15 minutes of our time together today. We will be asking for feedback throughout the presentation via Poll Everywhere as well. To get us primed for that real-time feedback, I'm going to ask you all to log into Poll Everywhere now and keep it up either in another window on your computer or on your phone, whatever you prefer, so you can answer questions as they arise. I'm going to drop this link into the chat for everyone to access Poll Everywhere now. We hope you'll share names as you log in. That'll be the first prompt you receive. But if you prefer anonymity, that is completely okay too. No names will show up in the results, so you don't have to worry about your comments being attributed to you in real time. It's all private. And again, if anyone has any trouble accessing Poll Everywhere or prefers not to use it, feel free to drop your responses into the chat box as well. All right, now that I've speedily gone through housekeeping items, let's begin. Today, we're going to be reviewing the high-level findings from a recently released report, which identifies a suite of best practices for producing trusted, validated hosting capacity analysis results reflecting real-world grid conditions. We'll begin with introductions to our panelists, followed by a short background on the report and its methodology before reviewing the categories of best practices, including business processes, quality control during the feeder model development process, validation of results before publication, followed by customer feedback and regulatory oversight. And then again, as I mentioned, we will end with a Q&A session with our panelists to get all of your questions answered. One quick note though, we will be distributing a follow-up questionnaire for additional thoughts and feedback at the end of the webinar as well. If there's anything that we missed out on that you want to include there, please do. All right, and with that, I will introduce Michelle Boyd, our program manager on this effort with the Department of Energy's Solar Energy Technologies Office. Michelle, thank you so much for joining us today, and take it away.
Thank you so very much. If you can hear me okay? Great, wonderful. So I wanted just to start by reminding people that the mission of the DOE Solar Energy Technologies Office is to accelerate the advancement and deployment of solar technology in support of an equitable transition to a decarbonized power sector by 2035. In order to do this, our projects and programs conduct research to reduce the cost of solar electricity, making it affordable and accessible for all, enable solar to support the reliability, resilience, and security of the grid, and support solar job growth and domestic manufacturing. The team that I lead at CETO, called the Strategic Analysis and Institutional Support Team, which is a mouthful, focuses on reducing the non-hardware or soft costs of solar, such as permitting and the topic of today, interconnection, as well as on developing solutions to other barriers to solar deployment. A hosting capacity analysis is one of those solutions. Interconnection requests for solar, energy storage, electric vehicles, and other distributed energy resources to the distribution grid is growing, as we know, very rapidly. But it is not always clear how much incremental capacity the system can accommodate. Grid capacity can be assessed through a hosting capacity analysis, which is a process used to determine the available capacity on the distribution grid for new energy resources without requiring expensive and time-consuming studies. It provides a snapshot of a distribution grid's current ability to interconnect these resources and helps inform utilities and regulators as they make decisions about grid investments. Hosting capacity analyses can streamline and add transparency to distributed energy resource planning and interconnection processes. There's a lot of promise here. However, a hosting capacity analysis must be performed properly, or it will not be accurate or reliable and therefore not used. And that's why the Solar Office supported this project led by NREL and the National Renewable Energy Lab in partnership with the Interstate Renewable Energy Council. I really want to thank this superstar team who worked together to identify procedural and technical practices for utilities, regulators, and other stakeholders to help overcome common challenges to hosting capacity analyses and make them accurate, trustworthy, and reliable. Finally, I would really like to urge all of you to sign up for CEDO's newsletter on our homepage to find out about all of our funding opportunities and information about our many other events. And I will drop the link in the chat. So I'm really looking forward to this webinar, and thanks so much for being here.
Thank you very much, Michelle. My name is Radina Valova, and I'm Regulatory Vice President with the Interstate Renewable Energy Council. And it's been a pleasure working with the CEDO and NREL teams on this project. And we are very grateful to all of the external stakeholders who have given their time and expertise to developing this paper. A little bit about IREC before I jump in. IREC focuses on building the foundation for the rapid adoption of clean energy and energy efficiency to benefit people, the economy, and our planet. And our vision is a 100% clean energy future that is reliable, resilient, and equitable. And we achieve these ends through engaging in 3 programs. That's electric sector regulatory reform, clean energy workforce solutions, my apologies, and local initiatives, which includes things like providing training on solar and storage for code enforcement officials. And NREL and IREC chose to engage on this project because, as Michelle noted, hosting capacity is an incredibly important tool for helping us get to a 100% clean energy future. And grid transparency is an absolutely essential way of helping to provide a more cost-effective and efficient integration of distributed energy resources into the grid. Hosting capacity analysis can also serve to make the interconnection process more efficient, and it can be used to more efficiently integrate DERs into proactive distribution planning. So it has many potential uses. But as Michelle noted, there are challenges associated with rolling out publicly available HCA data in whatever format it may be accessed, whether it's a spreadsheet or a map. And unfortunately, our early experience with publicly available HCA data is that some of the first published HCA data included inaccuracies. For example, a feeder showed 0 capacity, and once an interconnection application was processed, it turned out that that same feeder could actually accommodate multiple megawatts. And so there was a discrepancy between what the hosting capacity methodology was producing as a number and what the reality of the distribution grid was on the ground. And one of the biggest challenges is that with the early rollouts of hosting capacity analyses data is, in many of these instances, the utilities themselves didn't discover the data problems. It was hosting capacity analysis data users who alerted the utilities to these issues. And that's why it's so very important for us to make sure that as states and individual utilities are adopting HCA, that they do so in a way that maximizes the accuracy of the data so that it is developed with the ability to do that rather than trying to fix the problem later on down the line. And so NREL and IREC have both been engaged on hosting capacity for a number of years, both through numerous state regulatory proceedings in IREC's case and through research and analysis for both NREL and IREC. And again, we undertook this project to make sure that when utilities develop HCA data, publicly available data, they do it in a way that maximizes the accuracy of the results.
Thanks, Radina. Appreciate the introduction. My name is Yoki Zakai, and I'm an attorney with Schutt, Mahali, and Weinberger, and I'm here today representing the Interstate Renewable Energy Council. Thank you also to Michelle and Jess for the introduction, and you'll be hearing more from Adarsh in a few minutes. I'm really pleased to be able to present to you the results of the collaboration between IREC and NREL today. Can we get the next slide, please? Our report, Data Validation for Hosting Capacity Analyses, is available for a free download. Jess just put the link in the chat box, so if you haven't had a chance to take a look, you can get that for free now. In writing the report, our goal was to provide utilities, regulators, and stakeholders with a replicable roadmap to help HCA deployments provide accurate, trustworthy, and reliable results from the first day that they are published. To do this, we performed a literature review and interviewed industry experts. The literature review covered distribution system plans and HCA reports from utilities across the country. We interviewed HCA experts at utilities, software vendors, national laboratories, utility commissions, and DER developers. Building upon this research, as well as IREC's experience participating in HCA dockets at various commissions around the country, and NREL's experience performing hosting capacity analysis, we developed recommendations in 5 areas: business processes, quality control during the model development process, validating results before publication, feedback from customers and users, and regulatory oversight. Developing an HCA is a very time-intensive and resource-intensive process. Like any big project a utility sets out to accomplish, getting it right requires establishing appropriate business processes. So, our recommendations begin with best practices for business processes. Our first recommendation is appointing a single project manager to ensure that there's one person ultimately responsible for the HCA's success. The manager's area of responsibility would include performing the HCA, data validation, ensuring the accuracy of results, and improving the efficiency of the HCA process. The HCA manager's specific tasks would include identifying objectives for the team, providing strategic direction, establishing a standard structure for the HCA process and associated data validation activities, and documenting the standardized HCA process. We'll discuss many of these tasks in more detail later in the presentation. The HCA manager would also establish and monitor metrics. Our second business process recommendation is all about metrics. Establishing metrics to track the quality of input data and HCA results over time is important. I'm going to go over the metrics that we identified now. And if you have any other ideas for metrics that would be good to track, we're going to open up the poll at the end of this slide to take a look at what you've come up with. So feel free to put them in now as I'm chatting if you'd like. We identified the need for metrics to track the frequency of errors for each HCA update, the frequency of each type of failed flag or check for each HCA update, timeliness, for example, whether the team completed its processes in the desired time frame, and if the HCA was published on time. The number of recurring problems in the model building process, and with which source database that problem is associated with. We'll discuss more about this in the next slide. I want to emphasize one thing about the tracking of metrics. it's important to keep the data for each HCA update so that HCA managers and regulators can track if the process is producing fewer errors over time, more errors over time, or has hit a steady baseline. Now, let's jump over to the poll and see if there are any other ideas for metrics that we could add to this list. So we'll just wait for a couple seconds and see if folks want to go over to the website, which is at the top there, polev.com/webinars303. And if you have any other things you'd like to track, you can feel free to suggest them here. Great. Thanks to everybody who suggested some more metrics to track. I think we got some more good ideas. So let's move on to the next slide. Performing an HCA involves moving lots of data from source databases into feeder models that are used to perform the power flow analyses comprising the HCA. Source databases include distribution system asset databases, GIS databases, load databases, and generation profile databases. In the paper and in this presentation, we'll also refer to the load and generation profiles as customer consumption data. Errors in the power flow analysis used to perform the HCA are often due to data quality and integrity problems in these source databases. Efficient HCA processes fix identified errors in the source databases so that HCA engineers are not required to fix the same errors each time they use the source database to update the feeder model. Otherwise, engineers often develop a script or another automated solution to fix the error each time they use the source database to update the feeder model. To avoid the need to fix the same problem multiple times, it's a best practice for HCA managers to follow up with the source database owner when a root cause analysis shows that the source database includes inaccurate data or causes HCA errors. Our final business process recommendation concerns resources. There are two types of resources required to perform an HCA: employees and computers. Let's start with people. Engineers working on the HCA should have experience with their utility's distribution engineering practices, circuit models, and design standards. Engineers should be well-versed in the utility's planning and operation practices. More specifically, engineers should be trained to understand the HCA methodology, their utility's implementation of the methodology, and the flow of data from the source databases to the feeder model and then to the HCA software. Next, let's turn to technology. Using appropriate computational technologies, such as high-performance cloud computers, avoids unnecessary slowdowns due to hardware constraints and accelerates debugging. While portions of the HCA data validation program can be automated, engineers will always need to correct some problems. Effective HCA managers can consider how to strike the right balance between automation and manual work. Although scripting is a powerful tool and commercial software is always improving, effective HCA managers look for the point at which increased automation provides diminishing efficiency returns. Next, I want to go over the 4 broad stages of performing a hosting capacity analysis. These include model preparation, where inputs from the source database are gathered and the digital feeder model is built. Simulation, where power flow analyses simulate different scenarios, including increased DER penetration. Post-data processing. In this stage, HCA constraints are identified from the results of the simulations. Finally, the HCA constraints are published in online portals, including maps and tabular databases, such as APIs. We call this visualization. Can we bring up our next poll question? If you can head over to EV poll again. I'd like to know which stage of the HCA you think is most error prone of these 4. Okay, we'll give it another 10 seconds or so to see what people say. Looks like right now, model preparation is taking the lion's share of the votes with about 14% for simulation. Well, you and the HCA experts we interviewed for this paper agreed. Feeder model development is the most error-prone stage of the HCA. To address this, we've developed recommendations for creating repeatable and streamlined processes to check and correct model input errors at each stage in the HCA process. Adarsh is going to speak more about our recommendations in that area now.
Thanks, Yoki. Yeah, I was so happy to see the overlap between our finding and the attendees thinking the same. That's exactly what we found as well, as we spoke with many experts from different stakeholder industries involved. So quality control during feeder model development process. Given that we all somewhat agree to the point that most error-prone stage is model preparation, right? So here we'll be using the next few slides to share some selected practices, which are recommendations for using which we can have better improved quality control during the feeder model development. Let's start with a simple thing, right? So the need and the concept of hosting capacity analysis itself is intuitive and relatively easy to understand. However, what makes this process time intensive and cumbersome? That's a question. So what makes it complicated is performing hosting capacity analysis on few thousand distribution feeders again and again with maybe a few tens to hundreds of errors. That's what makes this process hard to follow through and track. With the recommendations already presented by Yoki, on top of it, the next few slides we'll be talking about will help you understand how best can we identify the root cause issues of model preparations so that you can have higher accuracy in your results. Next slide, please. It turns out that large portion of the hosting capacity analysis maps development process involves scripting, coding, which can also be referred to as software development or programming, depending on the intensity of coding involved. Coding involves a team of coders, maybe one person, maybe a certain project management, agile programming, could be any other idea. Another critical effort that's involved in hosting capacity analysis is pursuit towards automation, which is again enabled by scripting and coding. Developing scripts that are based on good coding practices are critical. Even in case of using commercial tools such as Sime, Synergy, DW, Windmill, there are many more commercial tools one can use. Even then, hiring and training engineers is critical. In case of homegrown solutions, in which means as a utility, you develop your own scripts and programs, which many utilities do. Good coding practices will save time in long term. Use code-based management tools, maybe such as GitHub, for example. Also using appropriate professional ideas such as branching codes, making edits, debugging the code to make sure it's good, then effective merging with the source database will help version issues, and also between the different engineers who add and modify scripts, there'll be a better streamlined process. Managing a central code base and having a central code base code manager, which includes training coding teams, will alleviate pain points in long term. Next slide, please. So let's start with the very first step in hosting capacity analysis, feeder model development. Everything starts with developing a model of the feeder. And this can be referred to as baseline feeder, which means the purpose is to accurately reflect the physical feeder that exists in the model, right? So we want to match the model with the physical feeder that exists. That's the first step. Confirming accuracy in the very first step, when we baseline the distribution feeder, avoids unnecessary work for the team later in the process. Suppose we do not accurately match or validate the baseline feeder, we will have wrong results at the last stage. In that case, we have to go back all the way and restart, which is time intensive and cumbersome. Next slide. Since as we were interviewing experts, we learned there may be few thousand feeders typically going through, or maybe few hundred at least, this process. Prioritizing the screening process is critical. Say you have a model already converted into your appropriate tool or software. You want to simulate them to make sure the feeder is accurate. You need to prioritize the screening process, which means it's not wise to run chronologically from Jan 1st to December 31st for all 1,000 feeders and then look at the errors. It's better to look at the critical load hours and fix the issues. Critical load hours may be summer peak, summer minimum, springtime maybe, which has low load and high solar. All these scenarios should be simulated first on the baseline feeder without adding any additional solar for what exists as of now. Then make sure you look at the key parameters, which you will look at in the next slide. Next slide, thank you. Once you have the baseline run for critical hours, then you can look at some of these validation checks. The table that you see on this slide is a set of down-selected attributes which a team can look at, can also automate so that one doesn't have to put too much effort. One can start looking at the voltage base. Typically, utilities, as they run through these, they look at per unit for voltage. That means you need to have appropriate voltage base that matches the value of your utility feeders. It could be 13 kilovolt, 12.47 kilovolt, 11 kilovolt, 4 kilovolt, 35 kilovolt, whatever, right? Whatever your value is, make sure it matches the substation value. You should also look at the nodal voltage violations at critical load periods. For example, you may have over voltage seeming to have issues around splitting time in your region. In that case, you should look at those times and see whether there are voltage violations at all that matches your local understanding. If you start seeing voltage violations at minimum load that you should expect, then it's good. If you don't expect any violations and you see them in your simulation, that's a checkpoint. Look for device overloads, including transformers and conductor thermal ratings. For example, you can look at transformer loading. For whatever reason, you see many transformers 150% loaded, which is not the scenario you were expecting. That can be a good checkpoint to go back and perform root cause analysis. Other parameter which is less talked about but very important is check the power factor at the feeder head at peak and minimum loads. Power factor is a ratio of active power to reactive power. You want to make sure there is right amount of reactive power being consumed by all the aggregate loads. If you see very out of range values, 0.7 power factor or very leading power factor, that means something is wrong in your load allocation and load values. Also make sure you check the aggregate power losses at the feeder head and overall feeder, and make sure you understand what percentage of load served and what percentage of that is the power loss. And make sure you look at the right active power consumption and the allocated peak load. Some of these can be automated, maybe most of these, and make sure you look at these before we can say something is good. Next slide. Moving on, once we have a baseline feeder, once we run critical hours, once we screen them based on some suggestions from the previous slide, here we can identify a standardized approach to resolving errors. Say you run 1,000 feeders and few hundred of them, or maybe 50, 10, whatever, may have issues. How do you screen them? How do you resolve these errors, right? That's the next content we'll be talking about. It's important to develop and follow a standardized approach to resolving errors. As validation checks is performed, it's quite complicated if you don't have a right approach. So that's what this slide is about. Our recommendation is that you can develop a tracking tool. A tool which is not too complicated, just an Excel sheet is fine. A tracking tool to help you monitor which and how many circuits that you have already checked or ran for are good, have passed, have produced warnings, have errors, have failed. Once you have an idea of how many feeders have issues, how many don't, then you can batch feeders with similar challenges and then have the team of engineers take advantage of the systematic and repeatable issues, and you can solve them together. For example, the tracking tool that we recommend could be as simple as this table. Once you run screening on selected feeders, you can look at how many of them completed and passed the stage. How many of them failed entirely, just stopped. How many of them completed, but with errors, could be voltage issues, could be transformers overloaded, could be having a bad power factor, higher losses than expected. How many of them just stopped, maybe because of some iteration issues or something else altogether? How many of them are in progress? For whatever reason, they're taking too long. So as you even make a little tracking tool as simple as this, it may help you. Then you can start batch processing them and take advantage. Once we have done this batch processing ideal tool developed, the next step is to look at root cause analysis. Say you have some voltage issues, or short circuit currents are too high, or your power factor is not good, or your losses are whooping 20%, right? So high. So in that case, how do you perform root cause analysis to resolve errors? That's what we'll talk about in the next few slides. As we interviewed and spoke with subject matter experts on this topic, we understood there are many ways to address this. However, one way we realized we can recommend and hope can help you all is we can streamline the root cause analysis by grouping issues into one of the 4 categories listed here. The issue may be coming because of topological errors, which means your GIS issue data can be wrong. It could be because of wrong equipment database. That means the database you have for transformers or regulators may be wrongly updated, may have outdated data, maybe erroneous for whatever reason. Maybe you have wrong conductor information. Could be the impedances are wrong. Or it may be that your customer consumption and generation data is wrong, which means your load allocation is wrong. So in the next few slides, we'll get into one level deeper to each of these so that we all have some clear understanding on these. Let's look at topology verification. Once you run, you see something is wrong in the feeder, you can actually go through this process very quickly. You can look for unintentional islands. Are there islands that are happening where electricity is not flowing because of a wrong conductor or a missing conductor or missing node, or a switch is unintentionally opened? Look at unintentional meshes. Not very few feeders typically have meshes in US utilities. So make sure meshes should exist or not. Look for incorrect phase loadings. This is a little complex to check for, but take a look at the voltage drop for each phase individually and see whether the variation and the difference between each phase voltage drop is not too far from what you should be seeing. Look for feeder switching states so that you can have the right configuration that you are running. Look for voltage correction equipment properly managed, and also make sure you have the existing DERs, solar storage, properly modeled. The second set of equipment verification, second set of issues you can look at is equipment verification. You can look for substation data and default settings. Make sure you have the right model of substation transformer. Should this be a load tap changer? Should this be fixed transformer? Take a look at it. Make sure you have the right impedances modeled. Make sure you have the right voltages. Take a look at the line regulators. Line regulators can have complex control settings. Take a look at the time delays. Which phase it is it connected to? Is it all 3 phase, individual phases? Take a look at capacitors. Make sure you have the right voltage triggers, time delays, control modes, seasonal variations properly modeled. Conductor verification is the next stage you can look at. Make sure you have the right impedances, which means you may have the right value, you may have the wrong unit. For example, capacitor can be Siemens or farads, right? So make sure you have the right values. Is it ohms? The line lengths are right. Make sure, how do you check for that? Because each feeder may have few thousand conductors. You can look for reactive power losses. You can look for circuit losses. You can look for voltage drop at peak load, short circuit currents. And all of this will help you quickly bucket whether the issue is coming from wrong conductor information. Last but not the least, rather very important, is customer consumption and generation profile verification. For customer consumption profiles, the best data set that we learn and also we recommend is using AMI, if you have AMI. AMI stands for Advanced Metering Infrastructure, as many of you may know already. It's typically used for billing purposes and fairly accurate. If one have AMI, then that's perfect. Although it may look effortful to pull information, but it certainly adds value. Other way to look at customer consumption is feeder head SCADA measurements, which is a common approach. Dividing feeder head consumption across all customer classes is an important part. Making sure that different customer classes, such as residential, commercial, industrial, having different customer consumption profiles is also important. The second component that makes a customer consumption is their generation, which is DER. They may have solar, they may have storage. Having the right value, right size, and making sure that the solar data that you are inputting is from your local area. If you have AMI, you have production meter, you can use that as well. If you don't, you can have local solar irradiance measurement monitoring, and you can use that. Compiling all this data is time consuming, but it's very critical we do it. Otherwise, the baseline is wrong, and then everything else we do on top of that will be wrong as well. Two proxy attributes you can look at to validate load profiles are active power allocation, which is you can look at how active power and reactive power are consumed and the ratio between them. And also making sure that the coincidental peaks for your locational feeders match what you are looking for. All in all, here is the next slide we came up with to illustrate how you can use all that we have been talking about in the last 30 minutes. This is an illustration. The way typically this goes is you develop a baseline feeder, and you want to make sure that baseline feeder matches what exists in the real world. How do you make sure it happens? You prioritize. You run selected critical hours, such as peak load, minimum load, or whatever hours you know are important to your local region. Then check for voltages, loading, circuit losses, reactive power at the feeder head, aggregate active power consumption. Check that, then follow a standardized process. You look at resolving errors, you look at batching the feeders that have similar issues. Once you have batched the feeders with similar issues, then do a root cause analysis. Look at topology, equipment, conductor, customer generation profiles. And then take a look at question 1. Is any source data erroneous? Is the issue coming from GIS? Issue coming from customer consumption data, SCADA? Issue coming from something that is a local database of your feeder utility that you're using? If it's yes to that, as Yoki clearly described, trigger a business process to fix source database. Then go back and rerun the baseline feeder, and then everything starts. If the issue is not the source database, issue is your scripts, which can be referred to as software as well. You need to fix that. Go debug it, branch out your code database, debug, fix it, then merge the debugged source code, and then recreate your feeder, again do the analysis. It's very critical we have these 4 steps very well validated. Although it takes time, it's important we go through this. Once everything is good, then we go with long-term simulations, scenario generation, such as adding more PV for hosting capacity analysis, and so on. This is one way to illustrate all that we have spoken in one slide. The next part will be about validation of results, and Yoki will be taking care of that.
Yeah, thanks, Adarsh. Next slide, please. So we recommend that after the utility performs the power flow simulation, it establishes a process to flag irregularities that will trigger a review before publication. This table provides a consolidated list of triggers and validation procedures. Most HCA experts we interviewed perform pre-publication reviews, but They noted that the feeder model building process is most commonly the root cause of the errors identified in the visualization and data publication processes. So I want to go over what's in the table for a second and just note that, it essentially just looks at, what are the results that are provided today? Are there any that are 0 or null? Or is there anything that's odd and duplicative? But at the end of the day, this is just a check before publication. And it's really the errors that will occur earlier in the process that you will then have to track down with the root cause analysis and fix. Next slide, please. We're going to look at customer feedback and regulatory oversight now. It's a best practice to accept feedback from users of the HCA. This is because customers can identify errors that the utility is unaware of and suggest improvements that the utility might not think of on its own. For these reasons, we recommend that utilities provide a mechanism to allow customers and HCA data users to provide feedback about their user experience, any errors identified, and the usefulness of the HCA data. Utilities can track the feedback they receive and report on any actions taken as a result of the feedback. Next, regulatory oversight. We recommend that regulators require utilities to prepare a data validation plan that describes the utility's data validation processes. The written plan should identify the HCA manager and describe the person's responsibilities, describe employee and computational resources devoted to the HCA, describe the utility's standardized approach to resolving errors, including the prioritized screening process and the processes used to verify the baseline model, feeder topology, equipment, conductors, and customer consumption profiles, and describe how the utility validates results before publication, as I just discussed. We also recommend that regulators require periodic reports of metrics that monitor the utility's performance and accuracy of the HCA results. The reports could include summaries of how many circuits have passed, produced warnings, or failed at each milestone in the HCA process, the results of the root cause analysis for recurring problems, and what improvements have been identified to fix those recurring problems. If the actions identified to fix the recurring problems don't fix it at the source, the report should identify the reasons why the problems could not be fixed at the source. And finally, you can summarize the feedback provided by customers. And with that, I think we're going to turn to questions. I can start. I noticed that Bernardo had asked the question about how much inaccuracy or percentage of an error is acceptable in the feeder modeling stage. I don't have a specific number for or percentage, but I do want to talk about metrics, which I just mentioned, which I think are really helpful. So if you're tracking the number of errors that you have at each stage and the root cause associated with each error, you can track in your updates if your analysis is trending to produce less errors at each update. And if you're identifying and resolving the errors at the root cause, ideally those metrics should trend down and you'll see less errors over time. Adarsh, do you have anything else to add to that?
Yeah, that's a good answer. Okay, I also responded to the question right there. Depends on the attribute. For example, for voltages, it's 1%, 2% is good. For active power, much less than that is good. So you look at the parameter, right? The circuit losses aggregate should not be more than what 4% in US, for example, right? So as you look at parameters, each parameter has a range, and an experienced engineer will be very quickly able to identify those and put those ranges in place, and then a buffer around that is what you look at. It depends on the attribute.
Yeah, great. Another question that we got a bunch of times, so I think we should take time to address, is which software is used to perform the HCA. And so I want to identify that at least in my work, I've seen the SIME and Synergy used most often, particularly because those are distribution modeling software in which you can both build a feeder model and perform an HCA analysis. I also see a lot of investor-owned utilities using the EPRI Drive software, but I would note that the EPRI Drive software doesn't build the feeder models, it just performs the hosted capacity analysis. So you'll have to use different distribution modeling software to build the feeder models, and then that creates an extra step to then transfer the feeder models to Drive for the analysis. And I know Adarsh has worked with a couple of other softwares for this as well.
Yeah, I guess you mentioned all. There are many softwares. Some utilities, use a software to convert GIS into a format that's usable for hosting capacity. Sometimes it's all interconnected. There are many homegrown solutions. There are many existing startup companies who are actually doing a great job in this too. May not be as popular as Synergy or SIME, right? So yeah, there are many tools one can use. Irrespective, the idea is asking the right questions. Whatever tool you want to use, go ahead. Ask the right questions, ask what you want for yourself, because the report explains very well on that. Hosting capacity itself is a topic, as you all intuitively understand, there are many details that make this very interesting. So understand what processes, tools you use, train your engineers, right? Those are the steps that are very important as much as what tool you use.
Great, and I'll answer a question from Brian now, who asked about HCA methodologies and if there's an agreement or standards. And the methodology used tends to vary based on the use case. I'd encourage you to look at one of IREC's recent papers called Key Decisions for Hosting Capacity Analysis, which goes into more detail on the various decisions that go into developing an HCA, including a discussion of the different use cases. And I'd note briefly that the most common use case we've seen so far is to guide interconnection decision-making. In California, the HCA is also used in the interconnection screening process itself, and the Minnesota Commission has established a goal to work towards using hosting capacity analysis in the interconnection screening process also. When you're looking at the interconnection use case as opposed to distribution planning or locational value, the iterative methodology is the most common one used, and EPRI's Drive tool labels this centralized methodology. So there are a couple different ways to say it. Adarsh, do you want to answer any of the more technical questions that have come through?
I see one question from Elder Romero, fuse ratings during HCA. So it's a very good question. Production, hosting capacity analysis, right? So hosting capacity analysis, as it's currently defined, do not look at production. Production settings happen afterwards because production doesn't change for every 5 kilowatt you add. So ratings are important, but the existing hosting capacity analysis tools do not do a fuse rating analysis for hosting capacity analysis. But what I meant by short circuit currents is understanding when there is a fault induced in the feeder, what are the currents that flow? And that helps you understand whether the conductor impedances are in the range or not in the range. That's what I meant. And these are the faults that are modeled, for example, any tool, OpenDSS or Synergy or Sine. If you conduct a short circuit, they put a deadbolt fault on different conductors from the first conductor to the last conductor and give you short circuit currents at different locations on the feeder. That's what I meant, not the fuse ratings. And generally fuse ratings are not looked at for hosting capacity analysis whenever you run this, and there's a separate process that's used for reconfiguring fuse ratings. And that's not done very often. That's one. Is there any other question, Yoki, that you?
If you want to keep going, that's fine. Otherwise, I have one that I can answer.
You go ahead. You can take turns.
Okay. Yeah, Stephen asked about small municipal electric providers that might not have personnel capable of performing the kind of robust HCA that we're talking about here. And, you know, I think this really comes back to, you know, the resources that each utility has. And there are a lot of consultants out there that are able to help with this type of process. And I know NREL has helped some utilities in performing hosting capacity analysis as well. And so, yeah, if, you know, if in-house options aren't good, I think there are, you know, there are consultants and other folks available to help out. I know of at least one consumer-owned utility, the New Hampshire Electric Cooperative, that took this approach and hired a consultant to perform their hosting capacity analysis. Why don't you go ahead with another question, Adar?
Yeah, I see another quick mention. Mainline fuse influences thermal evaluation also, correct? That's true. That's something that's very critical. It could be a mainline fuse, could be a recloser, could be different structures used. But yes, it's important we do that. And another question I saw about upgrading. When something is upgraded, I think it's by Harb Sidhu. As a conductor is upgraded, it's important we use the business process to make sure the GIS has the updated data. Then the hosting capacity analysis process is good. You don't need to do anything in your code base to address that shift or change. And whenever there's a utility upgrade of any sort, it's very critical the business process manager ensures that that sort of an update has been already done in the source database in the appropriate way. That will actually help in long term.
Adarsh, I see that Tyler asked the question that maybe you could answer. What do you mean by checking aggregate active power in the baseline model validation?
That means, okay, I can give you a simple answer, right? You have a feeder and you know the peak load is 3 megawatt based on your experience in the utility. Whereas as you allocate the load of that, say 3 megawatt across 400 or 1000 houses, it's important we double check it. As we allocate load that's supposed to be consumed at peak load across many distributed homes or commercial or industrial, the aggregate of all the consumption that's happening at all the houses and commercial and industry should match what you expect at the feeder head. That's what aggregate active power means, or what we are referring to as Hope it's not too confusing.
I know we're right at time, but we have one more question left, so I think we might as well get them all out. The last one was asking about calculating how much load can be added, such as from electric vehicles or maybe batteries that are charging from the grid or electrification. And I would point out that most hosting capacity software has the ability to evaluate the addition of loads as well as the addition of generation. But at least in California, where that analysis has been performed, we have actually continued to see some errors in the analysis. And so I would say that that is an area where this whole data validation process that we're discussing now still needs to be performed a little bit more, and to date, at least hasn't been the focus, and we've still seen errors occur in that process. So I think that there's room for improvement.
All right, I dropped some email addresses if there are follow-up questions into the chat for everyone, as well as that follow-up survey and questionnaire that I referenced at the beginning of the webinar. And otherwise, we just want to say thank you to everyone, including our panelists, for joining us today. Thank you so much. We will be emailing these links as well as the final presentation and the recording to all of our attendees today. Thank you so much. Have a good day, everyone.
Thank you very much.
Thanks for joining us. Bye-bye.